All right. Hello, everyone. Welcome to VSPG. Today we're hearing from Dr. Graham Shields on the Shuram anomaly, causes and consequences of global organic remineralization. I'll go ahead and introduce Graham for us. Dr. Graham Shields is a geochemist interested in the coevolution of life and Earth's surface environment through time, with a focus on the Neoproterozoic to early Cambrian, when complex multicellular life first began to dominate ecosystems. Graham and his research group worked to develop proxies to trace biogeochemical fluxes and related feedbacks that govern oxygen, carbon dioxide, and nutrient budgets on Earth. Their recent work has contributed to our understanding of how marine redox conditions influence the coevolution of life and its environment from the Ediacaran to the Cambrian, the impact of evaporate, weathering, and deposition on Earth's climate, and how we interpret rare Earth elements, in particular cerium anomalies and chemical sedimentary rocks through time. Graham received his bachelor's from Imperial College London and his PhD from ETH Zurich in Switzerland. He then started his postdoctoral career with a postdoc at CNRS in Strasbourg, France, followed by a research associate position at the University of Ottawa, a lecturer position at James Cook University, and a Humboldt Fellowship at the University of Munster in Germany. And today, he's a professor at University College London. We're excited to hear from you today, Graham. Please take it away.
Great, thanks, Alex. Thanks for that introduction and for the invitation to talk about one of my favorite subjects at the moment, the Shuram anomaly. When I look at this carbonate carbon isotope record that you're probably all very familiar with, what really strikes me is that if we look at the sort of the modern day, going back to the Mesozoic, despite the fact that there are numerous events, mass extinctions and glaciations and large igneous provinces and mountain building, the actual effect on the carbon isotope record is quite muted compared to, as we go back in time, to the Paleozoic, where we start to find some very large positive excursions. And then into the Neoproterozoic, things sort of go crazy with very, very positive excursions and very negative excursions, the most negative of which is the Shuram anomaly, which I will be discussing today. So there's two ways of looking at that. I mean, firstly, we could imagine that events were just larger. Perturbations to the carbon cycle were larger during the Neoproterozoic. I don't think there's much evidence for that. And we would imagine that negative feedbacks, which are part and parcel of the carbon, the global carbon cycle, would have kicked in. The second way of looking at that is that the carbon cycle had a much more elastic response to perturbations in the Neoproterozoic, or in other words, there were positive feedbacks that led to runaway perturbations to the carbon, global carbon cycle, and especially the carbon isotope mass balance. So I'm going to be focusing in large part on the Shuram anomaly, first discovered in 1993 by a group at the University of Bern working on the Shuram formation in Oman. But in the same year, it was also discovered in Siberia and in Australia. And since then, in the succeeding 32 years, has been found all over the world. The problem with the Shuram anomaly and the controversy surrounding the Shuram anomaly surrounds the fact that it is just so negative and it's really outsized compared to other negative excursions in the geological record, and so low that it actually is below the mantle value, which is often considered to be the input value. So just taken at face value, the Shuram anomaly suggests that there was a carbon oxidation event that lasted potentially for millions of years and would have sucked oxygen out of the ocean and the atmosphere. If we look at carbon isotopes in conventional sense, oops, I can't move forward for some reason. There we are. And we look at perturbations on 10 to the 5, 10 to the 6 million year timescales, we're going to have to look at a situation of mass balance, that in other words, the carbon entering the system is equal to the carbon exiting the system. And one of the first people to sort of point this out was one of the heroes of mine of Earth system science, Jacques-Joseph Abelman. This is a photo of him, and you can see his name inscribed on the Eiffel Tower today still. But in 1845, he came up with the same equations for this carbon mass balance that we have today. So in other words, the carbon sources must equal the carbon sinks, the carbon sources being volcanism, being the oxidation of fossil organic carbon, must equal the carbon sinks, which is carbonate burial and organic carbon burial. Just as we have carbon balance, we must also have isotopic balance. And so the carbon isotope composition of the input, as we can see here, must equal the carbon isotope composition of the output, if this is a genuine, authentic primary carbon isotope signal. And that output, as I've said, is organic carbon and carbonate carbon. If we rearrange that equation, we get the conventional carbon isotope mass balance. That the carbon isotope composition of aggregate carbonate deposited worldwide must equal this term on the right-hand side. And that should, and if we can assume this parameter, which is the discrimination between buried carbonate and buried organic carbon in terms of this isotopic composition, and we can assume the carbon isotope composition of input, which is normally supposed to be the bulk Earth or the mantle value, we can actually get this parameter, which is what we're looking for, which is the proportion of carbon which is buried as organic carbon. And that has a direct relationship to oxygenation, because carbon burial releases oxygen, and also to climate, because carbon burial removes carbon dioxide from the ocean atmosphere system. So it's potentially a very powerful tool, carbon isotopes. If we take this one stage further and we try to envisage this as a linear relationship, we end up with this purple line here. This is the line of isotope mass balance, where the intercept on the y-axis will be that last parameter, which is the input value. Now, this input value in models can vary. It can be higher, it can be lower. We actually don't know what the value is over periods of 10 to the 6, 10 to the 7 years. It could potentially be higher than -6 per mil or lower than -6 per mil, but that's often assumed that is somewhere around this value. And that's based on the carbon isotope values of things like inclusions in or diamonds and inclusions in mantle rocks. So with that, we can then take the isotopic value of all buried carbonate, assuming that is representative of the global carbonate sink, and we can read off the x-axis the proportion, the amount of organic carbon which is buried as organic carbon. If the values go higher, this is the aggregate value worldwide. If they go higher, then we have a greater proportion of organic carbon buried. But the problem with the Shuram excursion is that we have an exceptionally negative or exceptionally low isotopic value that reaches this input value or even exceeds the input value. If it reaches the input value and it is representative of the global carbonate sink, that tells us that there's essentially no organic carbon burial, which was the original interpretation of the Shuram anomaly by the University of Bern group. Or if it exceeds this value, it tells us that we have actually more net carbon oxidation than we have carbon burial. And it's very difficult to then sustain that for long periods of time. But we will get into that in a moment. So that's sort of the conventional way of looking at all long-term carbon isotope perturbations. So let's get into the Shuram anomaly itself. This is from the original paper in 1993. We can see a number of features of the Shuram anomaly here, which have been reported from other sections. Firstly is this hockey stick shape of the anomaly. So this is replicated in 4 different drill cores. And this hockey stick shape is often regarded as a response to eustatic transgression. So therefore, it is a condensation horizon, low sedimentation rates during sea level rise here, and then sort of a more gradual recovery. But in terms of time, there's a lot of time in this lower part, and there's sort of less time in the recovery part. So this is not a genuine time series. It is simply a depth series. there's been many, many interpretations of the Shuram anomaly. So I've just given you the conventional isotope mass balance. So that assumes that it is a real primary perturbation to the global carbon isotope mass balance. So that would imply global low net organic burial, or in other words, very efficient organic remineralization. However, there are many other interpretations that it is a diagenetic artifact and that these low values are not representative of ocean DIC or not representative of the global carbonate sink. There are interpretations of orthogenic carbonates, regional heterogeneity, ideas of carbon dioxide, again, heterogeneity in regionally marginal basins related to very high degrees of productivity. So these are quite unusual scenarios which would be kind of unique on a global scale in Earth history. But all of those interpretations, and I'm not going to go into them in detail, share one characteristic. They all show that the anomaly, or they put forward, suppose that the anomaly is not a genuine representation of the global carbonate sink, and therefore it is an artifact of bias sampling. So it's a regional sampling bias, and that makes no difference whether you're regarding it as diagenetic alteration or ocean heterogeneity. They're all telling you that there is a regional sampling bias. In my personal opinion, this is increasingly indefensible simply because of the sheer number of sections which span this interval of about 575 to 565 million years, and that they all show the Shuram anomaly in rocks of this age. And so it has never been demonstrated that there are rocks of this age that do not show the Shuram anomaly, and therefore it does appear to be representative of the global carbon isotope sink. And therefore, we have to then consider and explain it as a primary feature of the geological record. I'm going to introduce the Shuram anomaly with what I call three means, or sort of factoids. These are true to a greater or lesser extent, but they're often repeated from paper to paper, and I think they provide a nice introduction into the features of the Shuram anomaly, many of which it shares with other Neoproterozoic carbon isotope anomalies. The first one is that it's often been noted that there is a positive covariation between carbon and oxygen isotopic values in carbonates, and that is often interpreted as diagenetic alteration. That's because delta 18 can be decreased due to meteoric alteration or alteration at high temperatures. But as has been pointed out also numerous times, it is not diagnostic of diagenetic alteration. It is simply consistent with diagenetic alteration. And so this is one such paper where this was introduced. However, when you actually look at the sections that paper introduced, here's one of them from China, the Dongdahe section. You can see that the most extreme covariation of carbon and oxygen isotope values in China, at least, is from a section which is extremely shallow, extremely restricted. So these are anhydrite pseudomorphs, and is really quite unrepresentative of the other sections in China. So the most, and also it can be seen that as you can see in the recovery here, is that the very nice sort of positive covariation is very much mineralogy controlled, because dolomite is fractionated in a positive sense with respect to calcite. And so we really need to normalize for the mineralogy when we look at these sort of covariation. So here's an overview that we did in 2013 of 9 different sections, including the Dongdahe. So this is the covariation I was talking about. You can see that other sections, which are sometimes purely limestone, as in this case, sometimes mixed dolomite calcite, sometimes lagoonal situations or more open ocean north-facing situations. These are all very different types of settings. Fengtan is actually quite a deep distal succession. And you can see that the covariation either disappears completely, or where it's reproduced in purely calcite sections, what we see is that the covariation is reduced to perhaps 4 or 5 per mil, which can be nicely interpreted in terms of a normal climatic change of, let's say, 10, 15 degrees centigrade, which is it's much more in keeping with other information that we have from this period, that the Shuram was an interval of relatively warm conditions. But in other words, there's not a great deal of evidence left for diagenetic alteration, at least not systematic diagenetic alteration, but there is potential evidence for climatic warming. When we look at it more widespread, this again from the same paper, we can see that the Shuram anomaly is shown in many, many sections of the world. In most cases, we do see this hockey stick. We see sequence boundaries at its base, condensation at its base. But as in South China, there are also places where we have a much more of a basin-shaped feature. Eustatic transgression and shoaling upward is actually very common. It was pointed out in this wonderful paper by James Bush et al. 2022 in EPSL, where they considered all of the sections that had been looked at up to that point and showed that there was plenty of evidence for eustatic transgression at the beginning of the Shuram anomaly and shoaling at the end of the Shuram anomaly. Not only that, but also they identified a vertical gradient whereby shallower sections had more positive values, but still extremely negative during the anomaly compared to the deeper, more distal successions. And that's also what we found in China. The other thing that I take away from these sorts of studies is that there is a potential sampling bias. And so we can often, if we're looking at the representative value for the global carbon isotope sink, it's often taken to be -10, -11, or even more negative. Actually, this vertical gradient and the tendency for shallow sections to have more positive values suggests perhaps that we are actually sometimes exaggerating the negative value of the Shuram anomaly, and that the shallowest sections are more likely to have been eroded away during this shoaling towards, as we will see, towards glaciation. And so there's probably a good argument to suggest that the global average value would actually be at the top end of the Shuram, the common Shuram anomaly values, maybe -7 or -8 per mole. So much, much closer to the canonical mantle value than previously supposed. So shoaling upwards is also seen in this global stratigraphic calibration study by Fred Bowyer et al., and more recently by a similar study from Tom Hearing, where they identify the shoaling upward from the Shuram anomaly into this global low stand associated with erosion. And this is my point about sampling bias, that some of these sections will have eroded into and removed the Shuram anomaly. And that global low stand has been related to glaciation. So here we see primary evidence for terrestrial glaciation, this time in North China, at around about 555, 560 million years. And there's a well-known glaciation down here, the Gasquez glaciation before the Shuram anomaly. So we now think that there is the Shuram anomaly sits in a relatively warm period between two marked glaciations at around about 580 and 560 million years ago, associated with erosion. So the idea that there is a climatic component to the covariation is perhaps justified. And that's quite interesting when we think about positive feedback. So here's a great paper by Steve Stanley that really deserves to be looked at in more detail in terms of Neoproterozoic interpretations. I think people have looked at it in terms of much later interpretations of carbon isotope anomalies. It actually fits very well to Neoproterozoic scenarios. So this is looking at basically the temperature dependence of remineralization, in essence, anaerobic degradation by bacteria, and that at high temperatures we have greater rates of remineralization. So this is defined as a Q10 of 2.2, which means that for a 10 degrees centigrade warming, there is a 2.2 times greater respiration rate. And this is based on bacteria. Now, if we think about the Ediacaran world before the introduction of widespread bioturbation, etc., then bacteria would have basically ruled the respiration regime. So Steve Stanley says that there is a positive feedback that is generated by this temperature dependence, and as you increase temperature, the respiration rate will increase. You actually bury less organic carbon. So because you bury less organic carbon, you have more CO2 in the atmosphere, and therefore temperature will be hotter, and that leads to then a positive feedback whereby you then have even less organic burial. And so he actually interprets then a lot of carbon isotope anomalies of the Phanerozoic in this context. And I think it actually is a lot more applicable to things like the Shuram anomaly, where we can really see a good relationship between global climate change and the carbon isotope record. So this is potentially one source of the positive feedbacks I was talking about at the beginning. The second meme, if you like, is that there is no covariation, or very little, very seldom covariation between the carbonate and the kerogen carbon isotope records. And this is seen again right across the world. Not only that, but we actually notice that, so these are the banded limestone dolomite alternations that are typical of Gauche-Antwell member 3, where we see the beginning of the Shuram anomaly in South China. These are very TOC poor. And so there's very, very low kerogen contents, and the kerogen contents that do exist do not have isotopic values that reflect the low values of the carbonates in which they are found. This is from a study by Li Chao, and you can actually see that then in a figure. So the carbon isotope record shows the Shuram anomaly, or the DUNS as it's sometimes called in China. We can see that the kerogen values of these very low TOC strata don't really follow that trend, and that may be because they are older carbon, which are not representative of primary productivity, but it's certainly consistent with very low organic burial and effective remineralization. And then when we have the much higher organic carbon strata, the black shale here, we then do start to see some much, much lower values, which are reflective perhaps of the primary isotopic fractionation between DIC and organic carbon. But it's only in this recovery phase that we see that, and that is consistent with a very efficient organic remineralization story for the Shuram. We can see the same picture here in the Shuram formation. As I said before, there's probably a lot less time in this section, this part of the section, than in the base of the section where it's very condensed. We can see there's very little in the way of covariation at the start here, but there does seem to be quite low organic carbon values here during the recovery. And I think that's a sort of a consistent story of the Shuram, that the Shuram anomaly itself is often associated with very low TOC values, but if we do see covariation, we do see it during the recovery, and that is, of course, part of that consistent story. The fact that we had this, limited or no covariation scenario for the Neoproterozoic led to this very famous, or maybe some people think infamous, model, the Rothman ocean model, whereby the reason we get such low isotopic values is that there was a very large pool of organic carbon in the ocean, the so-called DOC reservoir, dissolved organic carbon, or particulate organic carbon, and is the oxidation of that organic carbon reservoir which is actually driving isotopic values lower than the canonical mantle value. But I'd have to, state again that that sort of depends on which input value we choose for the carbon isotope mass balance. So here in Lee Kump's sort of conventional story, the input value here is -5. I've mentioned -6, but this is not that far away from the global average carbonate isotope value of the Shuram in any case. And the size of that DOC reservoir really depends on what value you choose for this input value. But this is always in the background, this DOC model, that there was a dynamically reactive pool of carbon that was just sitting around. It's much, much bigger than the modern DOC pool. But as I say, it's not absolutely essential for understanding the Shuram anomaly if you just take it as a zero organic burial event. The third meme is that the sheer size, the sheer magnitude of the Shuram anomaly, and even if we just regard it as a zero organic burial event, is difficult to explain in terms of an oxygen budget. And that's because as we go into the anomaly, presumably we are oxidizing carbon, we're remineralizing carbon, we're not burying carbon. And even if we're not oxidizing a DOC pool, we're not producing oxygen from organic production directly. And that would consume oxygen, presumably consume sulphate, and that limits the length of time that you can sustain the Shuram anomaly to much less than its constrained duration, which is 6, 7, 8 million years currently. However, this is not a dynamic model, and if you inject sulphate or you inject oxidants into the ocean, you can certainly balance this oxygen budget. It's not an insoluble problem. And to actually solve the problem of this sort of oxygen consumption story, we sort of need to think about a much more dynamic situation akin to the sorts of situations envisaged by people like Bob Garrels and Bob Berner, so the founders of modern Earth system science, where they considered that to balance the Earth's oxygen budget on long time scales, we need to look at the complementary sulfide-sulfate and carbonate-organic carbon relations. So we need to sort of think about the sulfur cycle as well as simply the carbon cycle. And this is often called sink switching. So an imbalance in one cycle, the carbon cycle, for example, would be compensated for by changes in the sulfur cycle. And that's in a very dynamic way. So we're not just consuming oxygen, we're actually we're changing the fluxes. So how does that actually work in principle? So this is how you can envisage sort of the Garrels world in terms of a box model. So we have the reduced components of the carbon cycle here, the reduced components of the sulfur cycle here, the oxidized components of the carbon cycle on the top right, and the oxidized components of the sulfur cycle here. Organic burial, mole for mole, releases 1 mole of oxygen. So that's the oxygen produced by photosynthesis that then stays in the atmosphere because you bury the organic matter. But pyrite burial also releases oxygen, almost 2 moles for every mole of sulphate, which is reduced to sulfide and then subsequently buried as pyrite. This was the stoichiometry first worked out by Jacques Joseph Abelman in 1845, and we still think it's pretty much accurate. And that's simply because you don't consume the oxygen directly. You take the oxygen from the sulfate, and then that again allows oxygen to rise in the atmosphere. So in other words, if we are oxidizing rather a large amount of organic carbon, so that's this B flux, and that sort of exceeds the organic burial, and in the case of the Shuram anomaly, there doesn't appear to be a lot of organic burial, then that has to be compensated for by an equivalent change here. So in other words, if B is greater than A, that would lead to low delta carbon 13 and low organic burial. Then D, pyrite burial, has to be greater than C, and so there would be an oxygen surplus in the sulfur cycle to balance that. And that can be generated from the carbon cycle first principle or from the sulfur cycle first principle. The implication here is that G is greater than H. In other words, if we weather rock sulfate into the ocean, and we do not just cycle that back again as rock sulfate, and that is allowed then to become part of the reduced sulfur story, then we can generate that surplus and sustain it. So what am I talking about? This is another view of exactly the same model, and you can just follow the yellow arrows here. Rock sulfate weathering goes into the ocean, is removed as pyrite, And that sort of works because if you do not bury evaporites, so gypsum as evaporite, then you can sustain that surplus. You can have excess pyrite burial, so excess pyrite burial relative to weathering, and that can sustain efficient remineralization of organic carbon, even if you have no organic burial. It's just a case of how much you need. So pyrite burial is greater than pyrite weathering, and that is reflected as an oxygen surplus. So this is one way of getting around sort of the Bristow and Kennedy sort of unsustainable oxygen consumption story. And in conventional Garrel's terms, this is a sink switch from calcium sulfate to CO2. But crucially, we cannot bury the sulfate as evaporite. And in a low sulfate ocean, that may simply be predictable because we haven't reached perhaps gypsum saturation because of low sulfate values. So sulfate's going in, but it's being effectively removed. So in 2019, we did some modeling. We worked out exactly how much sulfate we would need. It sort of depends on how much of that sulfate input you actually remove as pyrite. So you can remove it all as pyrite, you can remove half as pyrite. And so you can then sort of read off this exactly how much gypsum input you would actually need. So we put the event range as between -15 and -8. But as I said earlier, because of sampling bias and erosion due to glacial eustatic sea level fall, it's actually this higher range, which is probably more representative of the global carbonate sink. So that makes the numbers here not dissimilar to the modern day sulfate input, riverine sulfate input. So it's certainly nothing particularly unimaginable, especially in the context of the tectonic events that are happening at this time. And as we pointed out in that paper, that the coming together of Gondwanaland, the aggregation of this sort of mega continent in the Ediacaran period would have raised the number of basins that contained gypsum, contained anhydrite, and that's because more than 1 million kilometers cubed of sulfate-rich evaporites are left today from this time period, and they would have formed in as Rodinia started to break apart. So this is the story of evaporites. It's very much a tectonic scenario that you get this regional accumulation of gypsum, of halite, either due to continental rifting, and then see the ocean sort of submerging these rifted margins, or in some cases due to tectonic collisions and basin restriction, as happened in the Messinian salinity crisis. So it's very much a tectonic thing, and it's kind of an inevitable thing as well. And I think this is something that we do need to take into account when we're talking about global carbon cycle perturbations of the past, that these sorts of events of evaporite deposition, but also evaporite weathering, and the resultant imbalances that that produces on the carbon cycle, they're kind of inevitable consequences of supercontinent cycles. And so I don't think it's inconceivable. So just to summarize then, before we go on and talk about some of the consequences, I think the consensus at the moment, if I can allow myself that word, at least my opinion, is that the Shuram anomaly was a time of a warm climate sandwiched between two increasingly evident glaciations, a time of high oxidant flux in terms of sulfate input, but essentially a time of effective organic remineralization and very little organic carbon burial. So in terms of covariation between carbon and oxygen isotopes, yes, it does occur, but it's relatively modest where it's not mineralogically controlled and could be related to warm oceans. There is no covariation between carbonate carbon and organic carbon, but that also would be expected by a time of low organic burial and very efficient remineralization. Both of points 1 and 2 are quite related to the idea that high temperature causes much greater respiration rates among anaerobic bacteria. And finally, low carbon isotope values imply an unconventional carbon cycle. It's also true, but the oxygen demand can be met when pyrite burial exceeds pyrite leveling. I think increasingly we are finding out now that some of the really classic fossil localities of the Ediacaran coincide in time with the Shuram anomaly. This wasn't even clear perhaps 5 or 6 years ago, but recent rhenium, osmium, uranium, lead constraints on the Shuram anomaly and its equivalent suggest that it lasted no longer than about 10 million years. It was somewhere between 575 and 565 million years ago. And these constraints are getting better and better all the time. But what's exciting about that is that they're almost exactly equivalent to the classic Avalonian Ediacaran fronts, so from Newfoundland and from England. And this is the time of when benthic megafauna, presumably aerobic, early animal ancestors, radiated into the deep sea, suggesting there was some degree of oxygenation of the seafloor. But anyway, conditions conducive to the success of these very, very early animal ancestors, some of which have been interpreted as the earliest eumetazoa. So here's sort of an example of those Avalonian fossils. This is from England, in Leicestershire, Charnwood Forest, and a number of paleontologists having a whale of a time looking at them. And what they're looking at is these rather large fronds, fractal, with their fractal geometries, some of which, including Charnia, have now been interpreted as eumetazoa, so genuine animals. And then by the time we get to like 560 million years, we're starting to get potentially crown group metazoa as well. There is some geochemical evidence that this radiation was facilitated by oxygenation of the seafloor, and that's based on ion speciation. So this is a well-known series of papers by Don Canfield, and we can see that deep water oxygen seems to occur, at least in Newfoundland, directly after the glaciation, and is coincident with this radiation of early animals. And some of which, as we can see, actually show evidence of being motile. And of course, mussels require oxygen. So there may well be a connection here between the Shuram anomaly and oxygenation of the seafloor. This is suggested by more sophisticated isotopic techniques like uranium isotopes, in this case, molybdenum isotopes. And we can see that the Shuram anomaly, in terms of molybdenum isotopes, starts to show modern-like extent of seafloor anoxia for the first time during the Shuram anomaly. And so this is a story which is ongoing, and more data is sort of is coming together to show that this was a genuine global oxygenation event. But it wasn't an irreversible event, as we will see in a moment. And there were a lot of fluctuations around this time. So watch this space. Sulfur isotopes also play a role here. So this is sort of unpublished work by Jerry, who was a PhD student of mine. And you can see that, and this is not an isolated study. I could choose many other studies, including from Shuram itself. You can see that the classic Shuram anomaly is found here. So this section is Shushan section. It's mostly limestone. And you can see that the sulfur isotopes actually change in parallel. So there is some covariation between carbon and sulfur isotope values. And this is sort of telling us that the sulfate concentration of the ocean was not particularly low. It was not sulfate limited, but the sulfur isotope values reach exceptionally high values afterwards and before. And this is certainly part of the story, because this is just one part of a story of oscillatory behavior of covariant carbon and sulfur isotope values, which is part and parcel of this idea of positive feedbacks. So there are positive feedbacks, runaway feedbacks, affecting not only the carbon cycle, but also in this case, the sulfur cycle, sulfur isotopes, oxygenation, and climate, all the way through this interval. And as Tianchen He showed in his study from 2019, This oscillatory behavior of co-varying carbon and sulfur isotopes actually continues all the way to almost the middle Cambrian, and is an exceptionally important background to the classic Cambrian explosion. So positive feedbacks are really key to understanding this interval. So what do we know now about the Shuram anomaly? It was a time of uplift and erosion. It was a time of warm climate. It was a time of higher sea level, potentially extensive seafloor oxygenation, but in some areas, strong euxinia at productive margins, such as in China. And it was also a time of radiation of aerobic animal grade organisms, these rangiomorphs, early animal ancestors. So it had consequences far beyond just changes to carbon isotope mass balance. So what caused some of these positive feedbacks? So I had a stab at this in 2019 and subsequently, and this is just a sort of a pictorial version of what I've been talking about in terms of the sulfate weathering stories, the uplift and erosion of sulfate into the ocean as ocean sulfate, and then a large proportion of that buried as sulfide. But crucially, the proportion of pyrite relative to the amount of sulfate flux is actually going down at this point, and that's where we get the lower sulfur isotope values. But overall, we have more pyrite, more sulfide burial, and therefore the potential for oxygenation and remineralization. Remineralization leads to higher carbon dioxide, and this is where Stanley's Q10 hypothesis comes in. That's a further positive feedback that then allows greater chemical weathering, nutrients, and eventually more sulfate weathering. And so we have a potential runaway situation of global warming. And net result is the Shuram anomaly and low ocean deep delta carbon 13. So I talked about the Shuram anomaly, and at least my view of the Shuram anomaly, and I think that's sort of reaching consensus in terms of those feedbacks. But how do you actually get out? How do you get out of the Shuram anomaly? Because we don't just have negative excursions, we also have returns and recoveries to much more positive values. Not only that, we also have returns to much colder conditions as well. So then we start to bury organic carbon, which draws down CO2, and we go to the other extreme. I think one of the key things here, and you can see this in the modeling that we did in 2019, is about the sulfate, the size of the sulfate reservoir. It's important for the temperature feedback, the positive feedback, that the oceans are generally anoxic, and it's important for this sulfur cycle feedback that the sulfate concentrations the flux is high, but the actual concentration in the ocean is quite low. And the reason for that is we don't really want gypsum to be precipitated out, because that would remove the oxidizing power. So there must be a critical threshold of sulfate concentration whereby pyrite burial is maximized, but gypsum precipitation doesn't occur, at least not significantly. And as we can see here, and this is repeated in the sulfur isotope values that I was showing, there's plenty of evidence that sulfate increases during the Shuram anomaly. There's a nice paper by Juan Cui a few years back where he showed that there were many sulfate precipitates all around the world in Shuram anomaly type equivalent sections, and that the sulfate concentrations are increasing through this period. So once we get to a certain critical point, and sulfate will then start to be precipitated out, we can actually work in reverse, and we can start sucking some of that oxidizing power out by removing that sulfate. And interestingly enough, that's exactly what we see. One of the largest evaporite or gypsum evaporite deposits is found just at the end of the Shuram anomaly, around about 550 million years ago, and it continues sporadically right the way through the Cambrian radiations, and those deposits are found in Arabia, in Iran, also in India, but also China and many other places. And this is the classic Shuram. So as we have the Shuram anomaly, the recovery of the Shuram anomaly, and then we start to find widespread gypsum deposition. And once you get gypsum deposition and sulfate has reached that critical point, then we cannot provide the same oxidizing power that we had before. And we start to bury then organic carbon and start reversing in the other direction. And we no longer have the imbalance of pyrite burial is greater than pyrite weathering. I was going to go through that, but I don't think I need to. If we look at then this in terms of the box model I showed earlier, we're simply just doing everything in reverse. Critically here, we are weathering pyrite sulfide, which of course we have to do. Ever since the great oxidation event, oxygen has not really been a limiting factor for pyrite oxidation. So this is a time of tectonic mountain building. It's exposing a lot of reduced sulfur and carbon to oxidation, and the sulfur will be oxidized to sulfate, whether we like it or not. And that sulfide weathering will take in 2 moles of oxygen, go into the ocean of sulfate, and if it doesn't come out as pyrite, then that will result in a net loss of oxygen to the system. And if it comes out as evaporate, then, as I say, that's a reverse scenario to the Shuram anomaly that I was showing. And the net result of that loss of oxygen would then be a greater burial of organic carbon, a return to anoxia, and a runaway feedback in exactly the other direction, lower temperatures, lower rates of respiration, and cooling. So a runaway feedback to cooling, and that's sort of exactly what we see. This return to anoxia has been shown by people like Fei Zhang and Rosalie Tostevin, who's my PhD student back in the day, and we can see that the return from relatively high, more modern uranium isotope values, modern seawater like, to exceptionally low values indicative of ocean anoxia is something which is quite it's quite convincing in terms of a return to anoxia. We can see that here too, with the higher values at the end of the Shuram and then the exceptionally low values after the Shuram. So there seems to be fluctuations, quite extreme fluctuations in both directions through this entire period. And that's becoming a very consistent story as a backdrop to the Cambrian or Ediacaran Cambrian sort of radiations, this sort of runaway climate change carbon cycle chain. So I've already shown you this just to show you that again, that once after the Shuram is over and we start to get the recovery, sort of go to the other extreme of glaciation and organic burial, higher carbon isotope values. This is not only this sort of climate carbon isotope relationship is not only typical of the Shuram, it's actually typical of most, if not all, of the famous carbon isotope anomalies of the Neoproterozoic. So here's one related to the start of the Sturtian glaciation. So just like the later anomalies, it is succeeded by cooling. And here we have sort of the latest unpublished compilation of data from Elias Rugen, who's my PhD student. And you can see in the 75 meters, which is transitional into the Sturtian glaciation in Scotland, you see a consistent story of quite low carbon isotope values. But once it starts to recover, we then get the first evidence of rafted ice debris, ice wedges, etc. And this is recorded in great detail and will come out as a memoir either this year or the very beginning of next year. So this is proposed as the basal cryogenian GSSP and is currently being discussed. But in any case, the scenario of negative carbon isotope values recovering to higher carbon isotope values and then moving into cooling is something that is seen in the classic snowball Earth setting as well. This is just to underscore these wonderful sections, because I haven't shown many field photos. This is one of my favorite field photos taken from a boat looking at the Garvalach sections of southwest Scotland. And what we can see here is a part of the lower moraine, the lower tillite of the Sturtians, the beginning of the Sturtian. And what we can see here is a massively sort of folded dolomite carbonate unit. You can just see the bedding here. And it's been folded over by glaciotectonics and incorporated into this diamictite, which on these islands is up to 1 kilometer in thickness and has been recently dated to cover the entire Sturtian glaciation. So it's really a classic area for glaciation. I just thought I'd show you that because I think it's a fantastic photo. Just shows you the sheer force of these ice sheets. And we can see the same scenario here. So this is a great study by Catherine Rose, 2015. And again, you see kind of similar to the Shuram, these really, really low negative values recovering. And as they recover, we find the first evidence of ice-rafted debris. So it's becoming a common scenario for at least 4 glaciations through this interval that negative anomalies transition into glaciation or global cooling. And that's sort of what I started with. And potentially a lot of these anomalies, not just the Shuram, are related to these positive feedbacks, some of which may be related to sulfur cycle imbalance or the temperature respiration positive feedback. Before I finish, I just want to underscore, if you like, why I think the sulfur cycle is very much worth looking at, especially in a Precambrian anoxic context. There is a fundamental difference between what we think of as the stabilizing negative feedbacks of the carbon cycle and the potentially destabilizing positive feedbacks involving the sulfur cycle. And that's due to a number of factors. If you like, consider what we know about the carbon cycle. Organic carbon oxidation is not congruent. It is very much PO2 dependent, so it can act, at least in the Precambrian, can act as a negative feedback on oxygen and on climate. And when we think about the silicate weathering thermostat, same principle applies, that silicate weathering is related to CO2, related to temperature, but it is essentially incongruent. So silicate minerals are seldom weathered to completion, and that can act as a stabilizing thermostat regulating climate. The other point to that is that carbonate minerals are saturated in seawater. So if we actually have greater rates of chemical weathering, then we have greater amounts of carbonate mineral burial. The sulfur cycle, by contrast, which is often looked at as a complementary cycle, especially in the Garrel sense, to the carbon cycle, is actually very, very different. The sulfur cycle is essentially involving congruent weathering. Pyrite oxidation is not PO2 dependent, since the great oxidation event. If we raise up a mountain, we will oxidize all of that pyrite pretty much. There's really no such thing as detrital pyrite in more recent times. But also anhydrite, gypsum, sulfate minerals are very easily soluble. So again, if you raise up a mountain, that sulfate will go into the ocean and can potentially perturb. It just brings oxidizing power into the ocean. And finally, sulfate minerals are also undersaturated. Pyrite formation is limited by other things such as sulfate availability, reactive iron, reactive organic carbon. So although we view them in a comparative sense, they actually are very, very different indeed. So I think that does need to be considered when we look at the Precambrian and particularly the predictable consequences of tectonics, supercontinent cycles. So that leads me finally back to where we started, the Shuram anomaly. So as I pointed out, in my opinion, It is the consequence of a global organic remineralization event led to global warming. There are probably other isotopic anomalies through this interval that experience some of the um, uh, same causation, and it seem to have the same relationship to climate change. So it's, in a way, it's quite simplistic that high values equal cooling and low values equal warming, but that's sort of what it's telling us. But it's also telling us that this Neoproterozoic interval, as predicted, Joey starts barking. As I pointed out at the beginning, this is an interval not of regulation, but of runaway positive feedbacks. And I think those positive feedbacks probably are related to some temperature respiration rate relationship, and also the effect of the sulfur cycle in perturbing the carbon cycle, which is just something intrinsic to the global sulfur cycle. And I think I'll leave it there. Thank you very much for listening.
All right, thank you, Graham. That was great. We're going to go ahead and start the question and discussion. You can raise your hand, finding the reactions button at the bottom of your screen, and the raise hand button is there. Or you can type your question into the chat, and the hosts will ask it for you. So Greg Ritalik was first. Please go ahead.
Oh, that was great, Graham. I really enjoyed that. It's particularly relating carbon cycle to sulfur cycle because we have gypsic and calcic paleosols through that entire interval. But my question, and I'm really going to have to think about that hard. My question though is something quite different. I see Nick Christie Blick is on this group, and of course we have both been studying those tremendous canyons in the Wanaka Formation, the Shura Wanaka anomaly, as we prefer to call it, the Wanaka anomaly, of course.
Yeah.
What is the role of 600 meters of sea level fall in the canyons in the Wanaka?
Well, it's a good question. I guess Nick is probably better qualified to answer that than me. But it's certainly consistent with eustatic sea level change. But I believe that's quite a controversy in this very specific situation. But this sort of erosion event would be exactly what we would predict. You know, with regard to both of those glaciations, the Gastiers and the Loire trend. And from Fred Bowyer's work, we can see that there is a global non-deposition event or erosion event around that time. So certainly, without talking about the specifics of the Wanaka Canyons themselves, because I've never worked on them, there's certainly evidence on a global scale of quite significant sea level drawdown.
So you don't think that just the fact that it was exposed as paleokarst for many millions of years could completely explain the Shuram anomaly and why it goes so long? Because the isotopic excursion in organic carbon is extremely brief, and it's in the canyon fill, quite near the top. So the perturbation from organic seems to be brief. The perturbation from carbonate might be an artifact of the paleokarst.
Oh, I see. Well, again, it goes back to my initial point about whether what we see in the record is representative of the global carbonate. And we find it in so many places in the world that we would definitely need to see areas where they have more normal carbon isotope values or even more positive carbon isotope values, but contemporaneous, and we just don't see that. So I don't see it being an artifact of any particular regional event.
Right. Okay. Thank you. Very stimulating.
All right, thanks, Greg. Shu Hai Zhao, please go ahead.
Hey, yeah. Thanks, Graham, for the. Can you hear me?
Yes.
Yeah. Thanks, Graham, for the excellent talk. I have two questions. First one, you mentioned that following the the ending of the Shuram is associated with the global anoxia, and you cited the uranium isotope as evidence. But the uranium isotope, the negative excursion uranium isotope from the upper Umkirk, from the Shibantine, and from the Kutterspit are at least 15 and maybe 20 million years after the end of the Shuram. The Shuram ended about 565, and those, the Shibantine and the Upper Umkirk, the Kutterspit is about maybe 545, 550. So at least I would say at least 10 million years, and I probably more like 15 or even 20 million years later.
Yeah, sure. These are long events. The Shuram itself is up to 10 million years. So these are very, very long oscillations, which perhaps get a bit shorter as we get into the early Cambrian, but the same sort of oscillatory behavior is also seen in the uranium isotope record through the early Cambrian as well, but with shorter intervals. So I would say we're dealing with a bit of a depauperate uranium isotope record at the moment. But there is certainly evidence of this oscillatory behavior, not just in carbon and sulfur, but also in uranium isotopes. So we'll see how that turns out in due course.
Okay. Yeah. My second question, and this is more sort of asking for clarification. Maybe you talked about it and I missed. You mentioned to get into Shuram, you need to, bury more pyrite, and the intuitive reaction to that is I would expect to see they see it as sulphate sulfur isotope to increase. Instead, you see a decrease in the Ca as sulfur isotope in both your models. So I wonder what the parameter, how you drive the seawater sulfate isotope to lower while you're burying more pyrite.
Yeah, I mean, the easiest way to bury more pyrite is to have more sulfate flux. Okay. If you just have the same sulfate flux, keep everything the same, and you just, let's just bury more pyrite. Yeah, then delta sulfur 34 should go up. And that may well happen, in other parts of the geological record. But if you're driving everything with an increased sulfate flux, then the delta sulfur 34 value can stay the same. It can go lower, it can go higher. I mean, I would argue it's more likely to go lower because you're driving everything with just a greater sulfate flux. So it's a proportional thing. So, as a proportion, you're actually burying less pyrite, less sulfur in the form of pyrite, and the sulfate concentrations around the Shuram time appear to be relatively high or increasing, and so that's consistent with a high sulfate flux, but a greater pyrite burial, but it is a lower proportion of the overall sulfate input.
Yeah, so if you want to maintain a low ratio, then you want to increase the pyrite, which is the denominator on the top. You also need to increase the sulfate burial in order to maintain a low ratio, right? Because otherwise, if you just increase the denominator and you do nothing with the denominator, the ratios are going to increase, and the sulfur isotope is going to increase as well.
You don't need to bury the sulfate. You meant sulfate, yeah, SO4. You don't need to bury the sulfate. It just increases in the ocean, and it increases until you reach the saturation point for gypsum, and then it will come out of solution. So that's sort of what we see.
Okay.
So that's sort of what's happening at that point.
All right. Thanks, Graham. It's great to see you.
Yeah. It's good.
All right, I'm going to ask, there's one in the chat that I'll read off, and then Jim, I'm going to pass handling of this to you, okay? And you can start with Ewan. But so the next one's from Nasser Yubi. Thanks, Professor Graham Shields, for your insightful presentation. I have a question regarding the Shuram anomaly. Could the anomaly be recorded in continental domains such as alkaline lakes? And thank you in advance.
I mean, the short answer to that is yes. If it's a global primary event, then we would imagine that the ocean atmosphere system is isotopically light, not just the carbonates. So we'd imagine the ocean DIC is isotopically light. We kind of see that as the more open ocean, deeper sections, they seem to be even more negative. So consistent with that story. So on the continent, we should also see the same thing. We also see it in the, it's a bit rough, but we see it in Von Cantel's study of the orthogenic carbonates in Newfoundland, which are also dominated by organic carbon remineralisation. We actually see extremely low values, but they are all offset. I guess we'd see something similar on the continent, but the challenge with a lot of this kind of study is to prove prove that you're looking at things of the same age. And I think there's a lot of messiness in the stratigraphic literature, in the chemostratigraphic literature, where people say, well, we have equivalent rocks, but they don't show the Shuram anomaly, etc. But it's extremely difficult to demonstrate that. If you're not using carbon isotopes as the stratigraphic correlation tool, what are you using? And there aren't many alternatives to that. So it's extremely difficult I could imagine it'd be extremely difficult in a lake or in a paleosol to actually demonstrate that they are of exactly the right age. But the potential is there.
All right, we can go to the next question if there's no comments on that. Yuan?
Hello. Yes, thank you very much, Graham. It's fascinating to hear. I was wondering if you could expand a bit more on the discussion about the timing of the origin of animal ecosystems, because you mentioned the apparent synchronicity with the onset of the Shuram and the Avalon biota and potential effects of oxygen. And I was wondering, given that the explanation you've provided for the termination of the Shuram seems to require a sort of similar amount of depletion of oxygen in the system. And yet, of course, animals clearly survived that perfectly well. How do you square that, the Shuram being an onset for these ecosystems, if the end of the excursion didn't do away with them?
It's very difficult to do away with things once they've evolved. I mean, mass extinctions kind of show us that animals adapted to, ideal conditions end up being marginalized in certain niches where they're not too hot and sufficiently oxygenated, and it's actually very difficult, but not impossible to survive any mass extinction. I think there's one answer to that potentially is that we do see evidence that animals, when we start to see sort of evidence for more sort of classic modern groups, bilaterians, they do seem to be limited to much shallower conditions later in the Ediacaran, and that could potentially be because of anoxia. I think there's some evidence of that in Namibia and elsewhere, that most of the ocean was quite anoxic, and so they're limited to the surface area. But also it's climate. If we're dealing with the Shuram being possibly a hypothermal event, as some people have pointed out recently, then the conditions in the surface probably not very ideal for animals, but they may well have been more ideal as we get to the recovery of the Shuram. And so during much cooler conditions, surface, more oxic conditions might actually be ideal. Of course, the competition would be more extreme because they're much more limited in terms of the extent. So the way I see this whole Ediacaran Cambrian radiation is a series of boom and bust of radiations into the deeper environment, and then restriction to the much more shallow environment during cooling and potentially more anoxic times. But essentially a repetition of oscillatory extremes.
Okay, thank you very much.
All right, we have an additional question from Catherine Giles in the chat, which is, thank you for the very interesting talk. Could ocean sulfate increase also come from the dissolution of salt diapirs? Salt diapirism is prevalent on several continents at this time.
Absolutely, yes. Yeah, if it's of sufficient magnitude to have an effect globally? Definitely. I mean, the salt diapirs have to have an origin, of course. They have to originated from a time when there was sufficient gypsum or anhydrite deposition, and it's not just halide. But there's plenty of gypsum in the Tonian and even in the Paleoproterozoic. So yeah, I think salt diapirs is certainly a possibility. Another thing I didn't mention is I would mention perhaps a longer talk is also the effect of anhydrite deposition in hydrothermal cells. So once you start oxygenating the oceans and you have gypsum deposition, it won't just be in margins, evaporitic margins. It will also be beneath the seafloor. A lot of anhydrite today is actually stored during hydrothermal exchange. But yeah.
Hey, Graham, maybe I ask a couple questions. It's kind of a long question, but sort of the model that you involve for sulphate, it's kind of similar to, somewhat similar to Lee Camp and Mike Arthur involved for recycling of carbonates. Sort of in their case, we involve it with sea level fall. You have sea level rise, but you sort of argue that, I guess, mountain building and recycling of sulfate. So which leads to question like, how do you decouple recycling of pyrite from decoupling of from recycling of sulfate? And also you should recycle carbonates, and maybe you can talk a little bit more about incongruent versus congruent weathering, because like if you increase carbon dioxide, you should be able to dissolve through acidic dissolution carbonates, so they should recycle. And pyrite, for example, also kinetically controlled in terms of oxidation. So I didn't exactly understood difference between incongruent, congruent weathering for carbon and sulfur.
Right. Okay. I think there were quite a few questions in there.
Yeah.
So firstly, the Camp and Arthur model is looking at the isotopic composition of the input, basically. So if you draw down sea level, then you expose carbonate platforms to weathering. So you have more carbonate input that would push the delta carbon 13 value of the input higher, and that just changes the base level of everything. And so you can just generate an isotopic anomaly in that way. It's hard to sustain because you can't sustain that imbalance of carbonate and organic carbon weathering indefinitely. But it's a fundamentally different model because it's changing the delta carbon 13 of input. Whereas what we are doing is we're actually changing the balance of carbon oxidation. We're not actually changing the isotopic composition of what is being weathered as such. We can just keep that as an average of -5 or -6 per mil. The Camp and Arthur model was like changing it to say -3 per mil, and then everything shifts 3 per mil higher. So it's a fundamentally different model. In terms of the incongruent versus congruent, I guess my point there is just the essential solubility of sulfate minerals. I'm not suggesting that carbonate minerals are not congruently weathered. I mean, when you raise a mountain, you will also dissolve carbonate, and that carbonate will go into the ocean. But that doesn't, in model world, that doesn't actually change the CO2 balance, because if you put calcium and alkalinity into the ocean, then you should bury calcium and alkalinity in the form of calcium carbonate. You don't actually have a net change in CO2. So the silicate weathering component is much more important in that sense. And so the incongruent weathering with regard to the carbonate relates to the silicate weathering and the silicate weathering thermostat, not to the carbonate weathering. But the sulfur cycle is fundamentally different, and because there is no equivalent to silicate weathering for sulfur. You expose sulfate minerals to weathering, and you just have more sulfate going into the ocean. You expose more pyrite to weathering, you'll also have more sulfate going into the ocean. So it is sort of a very elastic, it's a flux that can vary through orders of magnitude relatively easily during tectonic events. Whereas with the carbon cycle, that's not quite the same. So if you expose more silicate to weathering, you're still limited by the CO2 flux. Okay, you're not limited. It's not the amount of silicate minerals which is actually the limiting factor. Whereas with the sulfur cycle, that's just the case. So I hope that makes it a little bit clearer, but probably worth a discussion over beer.
So if you don't change a balance, don't you consume oxygen to oxidize pyrite in the same? And would it be a total increase in oxidizing power provided to ocean if you sort of consume oxygen to oxidize pyrite and release sulfate?
This is the problem of the sulfur cycle, is if you expose lots of pyrite to weathering, you will consume oxygen, and you need to get that back by burying the same sulfur as pyrite, and that would be a perfect cycle. So if evaporite weathering is balanced by evaporite deposition and pyrite weathering is balanced by pyrite deposition, then you can balance it. But you have to do that. There's no negative feedback that fundamentally regulates that process, and that's sort of my point. If you look at the Lomagendi event, I mean, seeing I'm speaking to you, let's move to that. I mean, it's a little bit like the recovery from the Shuram, because if you can imagine that during the Lomagendi event, you have, for the first time, substantial pyrite weathering, sulfates going into the ocean, that is consuming oxygen. But then the Lomagendi is synchronous to a very substantial evaporite deposition event too. And so you don't have a sulfate flux going into the ocean at that time. So you're essentially consuming oxygen by pyrite weathering, removing it as sulfate, and that is a net loss of oxygen to the system because you cannot balance it with sulfate weathering. So the way I see the sulfur cycle is that it sort of evolves step by step by step. These fluxes didn't all exist, and they came in one by one. So as soon as you have pyrite weathering, you cannot compensate it with a sulfate weathering flux.
So do you have any kind of interpretation how you preferentially dissolve sulfate and leave in pyrite on a continent? And it's, you didn't mention, but was a paper by David Fike in 2006, which has a lot of sulfur data and actually quite interesting with respect to what you're talking about, because in CAS, it shows increase in sulfur isotopes during Shuram excursion. Pyrite values don't really show change, and when there is a increase in difference, obviously, between sulfate and pyrite, which kind of...
I have to look at that again, Andrew, because I don't think it does increase. I think it's consistent with all of the other stories. I think there's quite a few sections in the world now where sulfur isotopes were looked at, and actually it all decreased during the Shuram anomaly. So I'm not. It's very consistent. About 20 per mil through the Shuram anomaly, and it's before it's about 40. It's quite extreme.
I open this paper, so it's before Shuram, it's around minus 20, plus 20.
Oh, you pyrite isotopes. Pyrite isotopes. Okay.
Oh,
not
pyrite.
sulfate.
Pyrite don't change. Yeah. But
pyrite is a very regional. It's a regional signal, but the sulfate should hopefully be of more global significance.
So for sulfate, it goes from maybe plus 23 to something like plus 25, plus 28.
Yeah, it's not a complete story, the Shuram sulfur isotope data from Oman. I think if you I didn't show it, but if you took a lot of sections together, there's some papers by Jake Kaufman on this subject. You can actually see a very consistent consistent pattern of much lower values during the Shuram compared to before and after. But you just have to believe me on that one.
Okay. And maybe just a quick question. So the most negative values that you see for Shuram, like we did some little bit work on backspin excursion, and typically you get most negative values either in organic rich shales or maybe in dirty carbonates. So what is your opinion, the most negative values in Shuram? Is it in clean carbonates and not associated with organic rich lithologies?
Well, the Don Canfield study, of course, shows that one extreme end member, because in Newfoundland there's very little carbonate. It's orthogenic carbonate and is presumably dominated by organic remineralisation. The values there from memory are, -20, -25 per mil. They're very, very low, but that's not pure DIC, of course. The lowest values in pure carbonate, -16 or something, in the deeper environments in China, like Fengtan section, etc. But I think sort of the classic averages would be like -10 or -9. So there's a wonderful study from Australia. The name's gone straight out of my head. By Husson, where they compare section to section, and it's extraordinarily consistent in the Wanaka from section to section. But usually it's around about -9. But as I said, with the Bush study and with our Chinese study, when you're in much more proximal settings, the values do tend to be quite a bit more positive, but still, -8 or so per mil. Whenever people have said, "Oh, it's much different," it's positive values, it's very difficult to correlate any of those sections stratigraphically to the Shuram interval. And apologies, I keep saying Shuram because people would often say Shuram Wanaka or Dunes, etc.
Okay, thanks, Graham. Maybe I'll let other people ask questions.
Thanks.
Did we had anything? Just Shuhei Zhao said thanks. Okay. Any comments? Paul, yeah, go. You're muted. You're muted, Paul.
There are a number of Tonian sulphate evaporite deposits in various parts of the world, so I think it's not inconceivable that one of those should be subjected to intense weathering for tectonic reasons, which would give you a big pulse of sulphate to the ocean, which could be timed with the Shuram. I think Graham has suggested that idea.
Yeah. Thanks for that, Paul. Yeah, I think it's an inevitability.
Yep.
Yeah.
Yes,
so it's the sporadic nature of evaporates that I like very much, is that they just come very rarely, deposited rarely, and probably eroded sporadically.
Starting from backspin, kind of evaporites keep increasing.
Probably one that's no longer with us.
Yeah.
Yeah, hard to know what has gone from the record.
Yeah. Well, it's there in a different in its isotopic memory.
Yeah, you could estimate that.
Oh,
yeah, good work, Graham. Thanks for remembering Steve Stanley.
Yeah, its time has come.
Yeah. Okay, I have to run. I'm traveling.
Okay.
Yeah, cheers.
Thanks. A last call for questions for Graham. Well, looks like we might not have more questions. Thanks, Graham. Thanks for stepping up sort of on a tight schedule. And next week we will hear from Susanna Porter, but I guess she will talk probably about Tonian, late Tonian, and emergence of eukaryotes. Okay, thanks everyone, and see you next week, Thursday. Bye.
Okay, thank you. Cheers. Bye-bye.